This video lecture is meant to continue the discussion about the quantum mechanical model, otherwise known as the Electron Cloud model, which developed out of uh, a problem with the Bohr model, in the fact that the Bohr model didn't explain all the observations of the behavior of some of the heavier elements that were known to exist and that they had studied. Bohr's model really only explained hydrogen's data. This model is really a mathematical model. It's full of all kinds of fairly complex mathematical equations that describe the probability where you can find electrons. And we're going to essentially stay away from the mathematical side of this model because it's really too complex for the scope of this course. So we're going to describe this model as qualitatively, as conceptually as possible. This model was put forth together by Heisenberg and Schrödinger, who really kind of described light, or described electrons' behavior in both sort of a particulate nature as well as a wave-like structure. And so that's getting a little bit ahead of ourselves. I'm going to go ahead and let this YouTube video try to explain a little bit about this model to get us started.
While neutrons and protons are small, electrons found swirling around the nucleus are even smaller. In fact, electrons are approximately 1/2000th the mass of a proton or neutron. While electrons are extremely small, they do have a charge, a negative charge. In atoms with an overall neutral charge, the number of electrons equals the number of protons. Electrons orbit the nucleus at extremely fast speeds. In fact, electrons may speed around the nucleus 1,000,000,000 times in 1 second. Scientists refer to the general space that electrons occupy as the electron cloud. The electron cloud can be thought of as similar to the space where bees are found swarming around a hive. Electrons are locked into certain areas within the electron cloud. These areas are called energy levels. Electrons with a relatively low amount of energy have their electrons located in energy levels close to the nucleus, whereas high-energy atoms possess electrons located farther from the nucleus. The arrangement of electrons in energy levels is very important in determining how an atom will interact with other atoms.
So the quantum mechanical model, we're going to try to simplify it. And you saw in the video the idea of the electron cloud, which is sort of like bees buzzing around the hive. You see here in this diagram from your book the nucleus where the protons and the neutrons are contained, and then a fuzzy region of space called the electron cloud. The diagram here says it's a visual model of the probable locations of electrons in an atom. The probability of finding an electron is higher in the denser regions of the cloud. So this electron cloud is a region where there is a 90% probability of finding an electron. And again, this is based on the mathematical formulas that were ascertained by Heisenberg and Schrödinger that we're not really going to delve into. We are going to try to substantiate this model a little bit qualitatively, so we're going to say that this model describes a mathematical probability that an electron will be found in regions called orbitals. So this idea of electron clouds, we're now going to stop referring to them as electron clouds, and we're going to refer to those regions, those clouds, as orbitals. And to give you an idea, this is sort of an overlay picture of the different kinds of electron clouds, the different kinds of orbitals that exist. They're all sort of superimposed on one another, and there are different shapes of these clouds. You can see here this spherical cloud, then there is this cloud that looks a bit like an infinity sign, and they all sort of superimpose over one another with the nucleus at the center. The biggest difference from the Bohr model is that these orbitals are not circular. There are some orbitals that are spherical shaped, but they are not. We are getting away from this planetary idea of the atom. So this idea of you might remember the Jimmy Neutron cartoon series that always showed the electrons whizzing around in certain paths. People are really still stuck on that idea of the atom, but this really is a little bit more further evolved idea of what the atom is like and where the electrons are in the atom. We alluded to this when we filled in our orbital diagrams, where each one of these boxes represented a different orbital, a different electron cloud, and this was sort of the organizational structure for where the electrons could be found. We used boxes to indicate the orbitals, but the orbitals themselves are not box-shaped. So we're going to try to give you an idea conceptually of these orbital shapes and more about what they're about. Going back in time here. So orbitals are defined as a region in space where there is an electron 90% of the time. Orbitals have different shapes. Any orbital can only hold 2 electrons maximum, so that's the idea with the 2 arrows in a box, each arrow representing an electron. And those 2 electrons must have an opposite spin. One electron in an orbital will spin clockwise, and the other one will spin counterclockwise to offset the magnetic effect set up by the clockwise spinning electron. We indicated this in our orbital diagrams by up arrows and down arrows. We alluded to the fact that orbitals have different shapes. S orbitals have a spherical shape. P orbitals have, I guess you could say, a peanut shape. D orbitals, I don't really know if you can say that they're diamond shaped, although I have had students express that, but to me the D orbital looks more like a 4-leaf clover, and the F orbital looks more like a flower. So perhaps that's one way to help you remember the letter representations of those orbitals. And those letters S, P, D, and F don't actually stand for sphere, peanut, diamond, and flower. There is sort of a name that goes along with those, but they're confusing, and I'm not going to mention them here. To give you a 3-dimensional idea of these shapes, I'm going to play this video that I found from YouTube, and I debated whether or not to play the soundtrack that goes along with this, but it's pretty funky, so I'm going to let you listen to it. So that was the S orbital, the spherical shaped. They're taking it away now so you can see the P-shaped orbitals. Notice that there's actually 3 versions of these p orbitals, one on the x-axis, one on the y-axis, and one on the z-axis. That was represented by 3 boxes on your orbital diagram. The d orbitals, there's actually 5 different orientations, and so they're going to show them to you one at a time.
Orbitals.
So this is the second one. This is the third d orbital. The fourth. And the fifth, which is definitely different from the other 4, but they all have different orientations around the XYZ axis. The F orbitals get very complex and they're not shown in this video. But here they are superimposed. There's the S, the P on top, and the D on top even further. So you can see each one of those orbitals represents an electron cloud, and just sort of funky, like the music that goes along with it. It gives you that idea that all those clouds are superimposed upon one another, with the very heart, the very center right there, is the nucleus. Stepping back, considering the big picture. So it turns out that there's 7 main layers of electrons, maximum in any atom. And those 7 layers are referred to as principal energy levels. And it's sort of a curious thing because each one of those 7 layers is added on every time you go down a row on the periodic table. A row on a periodic table is called a period. Therefore, that's why it's called the periodic table. And if you were to consider the long form of the periodic table, these are the 2 rows that are normally found underneath the periodic table, but they actually belong down here. If you take a look at this, you'll see here's row number 1. Let's call it period number 1. Here's period number 2 that goes across starting with lithium. Period 3 starting with sodium. Period 4 starting with potassium. Period 5 starting with rubidium. Period 6 starting with cesium. And period 7 starting with francium. So there's 7 rows that correspond to these 7 periods of the periodic table. So the connection to the fact that there are 7 principal energy levels is not coincidental. That's the reason why the elements were able to be organized so eloquently into the long form of the periodic table. Each of the 7 principal energy levels gets more and more complex because they kind of have to be, because you keep piling electrons on as you get to bigger and bigger atoms. The first principal energy level is only going to have one sublevel that's called that S sublevel, and that S orbital is that spherical shape. You'll see it here. If we show you right here, this principal energy level 1 denoted by the number 1, and sublevel S denoted by an S, of course. And there is only one orbital, one sphere, and so therefore on our orbital diagram we only showed it as a single box that can hold 2 electrons maximum. The second principal energy level, here I've abbreviated that as PEL, second principal energy level, will have 2 sublevels, the S and the P. The S sublevel is just like the 1S sublevel, except that it'll be a bigger sphere because it's got to be superimposed over the first S sublevel, the 1S. But the second principal energy level also has a 2p sublevel, which has 3 orbitals, 3 electron clouds. And these are the peanut-shaped ones that are in the different orientations around the nucleus of the atom. Here, those 3 orientations have been separated so you can see them individually. But in reality, each one of these clouds would be centered over each other, over where this plus sign is indicated on the first p orbital. So that's the second principal energy level. It has an S and it has a P. The third principal energy level, getting more complex, it'll have an S sublevel, it'll have a P sublevel, and it will have a D sublevel. So the third energy level will have this 1s orbital, it'll have the 3 p orbitals, remembering that you can put 2 electrons into each one of these orbitals. The d orbitals, the d sublevel, has 5 orbitals, and each one of these 5 d orbitals can hold only 2 electrons. Even though they look bigger, they can only hold 2 electrons for each one of these. So the d sublevel in total can hold up to 10 electrons. The p sublevel in total can hold up to 6 electrons. And the s sublevel, of course, can only hold a maximum of 2 electrons. Here we can see down here in our orbital diagram the 3s, the 3p, and the 3d sublevels. So those represent the orbitals of the third principal energy level. The fourth principal energy level gets even crazier still. It has an S, a P, a D, and an F sublevel. The F sublevel has 7 orbitals, 1, 2, 3, 4, 5, 6, 7 orbitals. Each one of these can only hold 2 electrons, so the F sublevel in total can hold up to 14 electrons. Now, the fourth energy level has a 4s, a 4p, a 4d, and a 4f. So these orbitals right here would represent the fourth principal energy level. And I think you saw already that even though those the 4s, 4p, 4d, and 4f are all part of the same energy level, there is some overlap in terms of how much energy they contain. For example, the 5s sublevel has more energy than the 4p sublevel, but the 5s sublevel has less energy than the 4d sublevel. So as you look on this arrow going up, this tells you kind of which sublevels have more energy, and it definitely gets to this weird overlap, which does have a pattern. It just gets a little complicated to follow the pattern. So to summarize, the S sublevel has one shape. It's a sphere. It can hold a maximum of 2 electrons, and it starts at principal energy level 1. The P sublevel has 3 shapes, 3 orbitals. They were the peanut-shaped orbitals, and they can each hold a maximum of 2 electrons, so the entire P sublevel can hold a maximum of 6. And you won't find p orbitals until you get to at least the second principal energy level, but you'll also find them in the third, the fourth, and above, and the greater principal energy levels. Sublevel D has 5 shapes, 5 orbital shapes. Each one of those 5 orbitals can hold 2 electrons for a maximum of 10 electrons, and you won't find D sublevels until they don't start until the third energy level. The F sublevel has 7 shapes. Each of those 7 shapes, each of those 7 orbitals can hold 2 electrons for a maximum of 14 total electrons for the entire F sublevel. The F sublevel you won't see that until you get to the fourth principal energy level, the fourth period of the periodic table. The electron configurations, we started writing these on our big pieces of paper. Electron configurations is really just the summary of how electrons are arranged within the orbitals of the atom. They look like this: 1s2, 2s2, 2p6, 3s2, and you can actually identify an atom from this alone, right here, if you count up the superscripts. 2 plus 2, that's 4, plus 6 is 10, plus 2 is 12. 12 electrons. Now, if we assume that the atom is neutral, then 12 electrons means we'll have 12 protons. 12 protons means we have magnesium. So electron configurations alone can help us identify neutral atoms. But even this shorthand can be abbreviated even further, because you can imagine that these electron configurations can get really long with the bigger elements. But magnesium is just 2 electrons greater than the noble gas neon. And so there's a shorthand version of electron configurations where if you have magnesium, which is just 2 electrons above or past noble gas, you put that noble gas symbol in brackets like so, and then you just write the electrons that are outside of neon's configuration. So this is just sort of a convenient way of shortening down those electron configurations. Now, there's 3 rules with electron configurations that you've already put into practice, but now we're just going to put names onto them. When you're writing electron configurations, there's an Aufbau principle which says that electrons enter the lowest energy level first. That means if you have 10 electrons to place into an orbital diagram, the first electron has to go into the 1s sublevel. All right. We always assume that atoms are in ground state when we are writing our electron configurations, which means that those electrons go into the lowest energy levels on the orbital diagrams. There's a Pauli exclusion principle that says at most 2 electrons are allowed per orbital, and each one has to have a different spin. You've already done this with our orbital diagrams when you put the up arrow and the down arrow, and that you only put 2 arrows total in each box. That's just has a name. It's called the Pauli exclusion principle. And then there's Hund's rule. Hund's rule says that when electrons occupy orbitals of equal energy, they don't pair up until they have to. This is the instance where we put, for example, in a p sublevel where there are 3 boxes, 3 orbitals, we put 1 electron in the box all the way to the left. The second electron went into the middle box. The third electron went into the box all the way to the right. And only if you had 4 electrons or more did you start pairing up the electrons in those 3 boxes. So Hund's rule, when electrons occupy orbitals of equal energy, they don't pair up until they have to, until there's at least 1 electron in each of those orbitals within that sublevel. All right, so this has been a lecture about electron configurations and the quantum model and how the S, P, D, and F sublevels all fit together. Thanks for staying tuned, and we'll see you in the classroom.